you start the recording, I switch off my cam, and you just try to start it. Okay.
Yeah.
Okay, I think it is running.
Yeah, it is.
Okay, perfect. Then I start the lecture and you copy the file afterwards to the chat. Okay, welcome to our lecture in Fluid Energy Machines, part 3 about combustion engines. And we want to start our lecture, and I have a small question about what do you think, how much energy is used as heat and how much energy goes to the road, or how much energy can be used mechanically if you have a look at the total overall energy inside the fuel. Here is the total energy from the liquid fuel or from the natural gas that should be used in the combustion engine. And you might use a lot of energy, about 60% is used for production of heat. Yeah, so you have exhaust gas losses, it's about 20 to 30%. You have cooling and radiation losses, and it's also about 30%. So if you don't use the heat, you have to use you can at least use 30% for mechanical work. And here you also lose a lot of energy. Yeah, you lose aerodynamic resistance energy, rolling resistance, you lose energy for braking. And roundabout, we can say, if you drive with your car with a combustion engine, you might use about 20% of the energy for driving, and the rest of the energy will be lost. Okay, and that's a lot of loss. Yeah. How can you calculate the real engine power from a combustion engine? You can, the power, we use a simple P. You can use the torque, and here the engine speed, as the angular frequency. You multiply the angular frequency with the torque, and you get the power. Or, or you can use. That's not good. Something's happening. Shift a bit. Yeah. I think something happened to the formula editor. Does not look so good. I clicked to the formula. That was not really cool. Okay. So now the arrows are not at the right position. I'm sorry for this. I will correct it. But you can use the engine speed. You can use the, I have to correct the, I think in your slides, the arrows are at the right position. You can use the displacement of the engine. You can use the engine speed. You can, if you have the fluid properties of the air, the density of the air, and the lambda values and the heating values, you can calculate the power of your engine. And please mention, density of the air can be changed. Yeah. Normally, the density of the air is about 1.22 kilograms per cubic meter. But how can the density of the air be changed if you drive a car or airplane? You can use a turbocharger. If you turbocharge your engine, you get higher densities, and so you get higher power at the engine. And the turbocharging was invented normally for airplanes. when the airplanes fly into a higher altitude, the air is much thinner and you have to compress air to get the right density. Okay, here you can see.
I'm
Yeah,
sorry, Mr.
Mr.
Rückert, I
Luther, yes?
have a question on the
Of
last
course, yeah.
slide. Yeah.
Mhm,
The letter I, where you say it's 0.5 for a four-stroke engine and 1 for a two-stroke engine.
mhm.
How does that compare to the letter TZ that we had in the last lecture? Because there was, I think it was T, and it had the number 2 for four-stroke engine and number 1 for a two-stroke engine.
Yeah, but this was it was just the reverse value. Yeah.
Okay.
In the last formula, we divide it by the factor, and here we multiply by another factor. But it's the same. Yeah. If you
Okay.
divide something by 2, you get 0.5, or if you divide something by 1, you get 1. It's the same.
Okay.
Yeah.
Okay, well, there was a formula where I was used and I was not sure what it is. I think it was with the mean effective pressure, but yeah, okay, understood.
Yeah, here you can, yeah, that has something to do with the ideal gas law. Yeah, you can insert the pressure, or you can just calculate use the ideal gas law, calculate the density depending on the pressure, and then you have the density. It's the same formula, yeah, more or less. It's just here the ideal gas law is already included, and the factor is just not 1 divided by the factor TZ. Here we just multiply with 1, but it has the same meaning. Yeah,
Okay.
you can use both formulas more or less. Yeah? And, and do you know where this factor comes from for two-stroke and four-stroke engine?
I guess it has to do something with how many revolutions the engine can do with one stroke.
Yes, you can. Maybe we go to the next slide. You can see it here really good. Yeah, this small GIF movie explains it really good. If you have a four-stroke engine, you have also the Seiliger process in the PV diagram, but every second stroke is used for cleaning. Yeah, you suck in the fuel, then you have the explosion, you produce the work, but in the second stroke you have to clean the cylinder. Yeah, it's like a pump. You have to clean the old gas inside the cylinder. And who does this work? It is done by the other cylinders. Yeah, if you look, Mr. Luther, if you look here at the cylinders, yeah, if one cylinder is opening, the other one is closing. Yeah, so you need always work. You need always work to get the wheels turning, and to also you need the work to clean the other cylinders. Yeah, and in the four-stroke engine, only every second stroke is a working stroke, and the other stroke is always a cleaning stroke.
Mm.
Yeah, it's like then the engine works like a pump, more or less, yeah, to clean the cylinder. So but that's also the explanation why you always need more cylinders. Yeah, you can't use only one cylinder. You have to use you need more cylinders. Yeah,
Yeah, that but also for counterbalance, isn't it?
for counterbalance also. Yes,
Yeah.
that's another point. Of course, you might know, as more cylinders you have, as better is the engine. Yeah,
Runs more stable.
yeah, runs more stable, has a lot of more power. Yeah, you can imagine if you have here, if you see this crank. Yeah, if you imagine you only have 4 cylinders. Yeah, one is pushing, the other is pulling, and this is cause of many um, many um, vibrations. Let's say it causes a lot of vibrations. Yeah? But if you have more cylinders, it runs more stable and it runs more smooth. Yeah, driving is much better if you have more cylinders. If you might look at a Bugatti or a big or a big Ferrari, they have a lot of cylinders and they run really smooth. Yeah. But there's another disadvantage if you have more cylinders. Yeah? If you have more cylinders, the disadvantage is that something can be damaged. Yeah? If you have more parts, more moving parts, the danger of damage is much higher. Yeah? We even have cars that can shift on, shift off cylinders. If you, for example, take a big Mercedes S-Class, yeah, an S-Class Mercedes can switch off cylinders, and then you can drive with less cylinders. Yeah. Okay, maybe if you don't, if you say we want to save a bit of fuel, then you can shift off some cylinders. And your car will also run if some cylinders are damaged, yeah, but that can happen. But if you have more cylinders, it will not work so good, but it can work. Yeah. The trend more or less is that we want to have less cylinders, yeah, because you need more fuel. Yeah? If you have more cylinders, you always need more fuel. That's a problem. Okay. Yeah, it's interesting topic. Yeah, of course. This design of the crank is really complicated. There can be a lot of different designs and also firing orders. Yeah, here you see a firing order 1, 3, 4, 2. That means the first cylinder will be fired first, and then the third cylinder will be fired. Afterwards, the fourth cylinder will be fired, and then the second cylinder will be fired. Yeah, that's sometimes a bit complicated. Okay. Okay. So and the firing order is in every engine different. Yeah, depends on the design of the crank. Okay, and here you can see a nice engine. It's a modern common rail diesel engine. Yeah. And you can see different parts. You can see the rail, the common rail. Okay. So let's have a bit closer look at the different combustion processes. Yeah, we can have homogeneous combustion and we can have so-called stratified combustion. If we have homogeneous combustion, here you see it's a picture of the cylinder of the engine. Here you can see the valve. It is a gasoline direct injection valve. Yeah, it's not a diesel. It's a you can see clearly that this is not a diesel engine because you have the spark plug here. Yeah, and you have the valves here. The air comes inside through the intake valve, and the gasoline will be injected into the open cylinder. Everything will be mixed, and then you have the compression and the working cycle. On the other side, you can have so-called stratified combustion, and this is really late combustion. It is also a direct injection, so it's not injected in the manifold, but the injection will take place at a really late moment when the compression is already really high. Yeah, then you inject a bit gasoline, and you have a swirl, and the swirl must really be planned that it reaches the spark plug. This is a bit more like a diesel engine. It is a gasoline engine, but it is, yeah, the strategy is a bit like in a diesel. Here you can see our cycle. Yeah, it's ideal. It's a combustion cycle. It looks a bit like a Seiliger, like the ideal Seiliger process, but that's a real pressure pressure volume diagram, and you can see what is important here. At first, we need, of course, important is the work. Yeah? And work is always the integral value of in the pressure volume diagram. So here we have the pressure volume diagram. So the work will be the area under this curve. Yeah, that is the work. And how can you influence this curve? Do you have any idea? How can we influence this PV diagram when we sit in the car? Do you have an idea? Mrs. Lindberg, do you have an idea how we can influence this diagram when we are in the car?
Not so sure, but no, I don't know.
Yeah, you can. It is, yeah, of course, it's difficult if I ask you in this way, but I think you know it. It's you can
Pressing the gas.
by pressing the gas pedal, of course.
Okay.
If you press, that's why we call it gas pedal. If you step with your foot on the gas pedal, you get a high area. This diagram goes up, you have a high area. And if you just in a lower cycle and you do not press so much on the gas pedal, this diagram is much smaller. Yeah. So the area under this curve is influenced by stepping on the gas pedal. And here at the bottom, we see a small, it looks like a line, but if I zoom in, it looks like this. And this is a cleaning cycle. Yeah, we do not get any work by the cleaning cycle. Yeah, that's nearly no area under this curve, because there's no combustion inside. Okay, and we calculate it by the integral of pressure. Integral is a curve under the diagram. Okay, and there's this EMAP number. We can calculate the work and divide it by the volume of our cylinder, the bit characteristic value. And we can have a brake mean efficient pressure. So what is a mean efficient pressure? If you look at this diagram, the diagram looks a bit complicated. Yeah, if I ask you, how much do you step on your gas pedal, and you want to explain me this diagram, you need a lot of time. Yeah, so we make it a bit easier. We just calculate one mean pressure here inside the diagram, and then the engineer can just talk about the mean pressure if they want to characterize this complicated diagram. Now that's in more easy value to explain how much you step on the gas pedal. And of course, you can calculate your efficiency. And the efficiency is the work that was given by the engine divided by the chemical energy or the heat of the reaction. Okay. Look a bit more deeper at the internal combustion engine. If we use a cylinder, we need a gas change. Yeah, fresh air has to enter the cylinder from the position of the intake valve, and maybe in old engines there was already fuel mixed in this fresh air stream, but you can also inject it inside the cylinder. That's more modern. I think if we have newer cars in the future, all the cars will change to direct injection. Only the old cars will remain and have port fuel injection. Okay, Then inside the cylinder, we get turbulence. We get a tumble, we call it a tumble, and the tumble can also influenced by the piston here. If you look at this piston, it looks really flat, but at modern cars, it can have a complicated geometry. Maybe I go back. Here you can see the piston. It has a really special design. Yeah? And designing this piston, there are many different designs here. They should influence turbulence. And you have here your fuel injection inside the cylinder. This is a direct injection engine, and you get your mixture. Okay. Then we look at a high pressure loop. Yeah, this is a gas exchange, the gas exchanges. But now if the fuel is injected and we get a higher pressure because of movement of the piston, you get combustion. You get an ignition front, you get ignition from the spark plug and a moving flame front. And the flame front is moving inside the cylinder volume. You have unburned gas, you have burning gas, and you can imagine if the burning process is really good, you get less emissions. But if the burning process, if the design of this process is not really good, you get a lot of unburned gas. Maybe you know it from motorbikes, you smell it, or sometimes small chip engines, they smell really like unburned hydrocarbons. Okay, and then you get your work on the piston. So we have different problems. We have fuel injection, we have mixture formation, we have turbulence. Turbulence is a big business in all fluid energy machines. Turbulence is always, normally you don't want to have turbulence so much. We will also come to the windmills, to the wind turbines, and you will see turbulence always, will lower the efficiency of all the fluid energy machines. But that's nature. Nature is turbulent, and it's not always straight as you like to have it. We have combustion and of course emissions and efficiencies. Have a small look at the thermodynamics. You're all experts in thermodynamics. You had it, you had it as an maybe question to our Finnish colleagues. You already had thermodynamics in school or university?
Yeah, we did.
You did. Okay, then everything is clear for you. So we have internal energy. And you know, the most important law in thermodynamics is the ideal gas law. Yeah, that's really important. You keep it in mind. You need it if you want to understand the combustion engine. Okay. So you have your burning rate, you have your work. Yeah, that's the integral value of P times volume. You have your heat loss, and you have all the different energy fluxes. Okay, that's it. Let's come to the different systems. I explained you currently most of in the future, in the near, I met a friend of mine at the weekend. I telephoned with him, and he works still at Bosch in the direct injection, and he told me, I think in 4 or 5 years, all the cars will be direct injection cars. No more port fuels anymore. Yeah, there's a big revolution now in this engine design. Here you see an older port fuel. Yeah, you inject the fuel directly into your port fuel. Then you get here, the valve opens and you get the mixing. that's not an ideal process. Today, we have injectors that inject directly in the cylinder, and you should design the design of the spray plum is really sophisticated. Every customer needs a special design. And this was a product I have designed at Bosch. It's a hard F5 valve. And you see here some complicated spray hole pattern. You see the different holes, and even inside the holes have different diameters. The holes have different direction. So you try to design a spray for your piston. Yeah, you don't want to spray on the spark plug. You don't want to spray on the walls, because all this means losses in efficiency, losses in gasoline. It's really important to design the spray for your demands and your engine, and every customer has a different design. Okay, you can have electric pumps for the fuel. Here is this all port fuel. Design of such a valve for the EV14 valve is not so complicated. Yeah, you just inject the fuel into the port fuel and it mixes by its own, more or less. Okay, here you see the rail. You maybe know the rail, a common rail from diesel common rail engines, but in modern gasoline engines they also have a rail to suppress fluctuations, pressure fluctuations inside the gas line. And here is a pump. It's a HDP5 high pressure pump from Bosch, and it's used to get high pressures of about 200, 300 or even 400 bars. Okay, have a short look at the ignition. How can the fuel be ignited? We need a spark plug. Here we have a nice spark plug from Bosch. We have I have a lot of pictures from Bosch. I took them from the internet, but it is true, Bosch is a really big supplier for cars, and many different engines use Bosch cars. I think Bosch is the biggest supplier for this parts worldwide, and most of the engines really use Bosch parts. Yeah? There are only a few competitors in this field. You have the spark plug here. You ignite the engine. You need an ignition coil, yeah, to spend the electricity, to spend the current to the spark plug. And you need, of course, a battery to get the electricity. This is a lead battery. And you also need a ECU, an electronic control unit, to give the signal to the coil to get the spark. And this looks easy. Yeah, it's electrotechnics. It looks easy. And you might say, yeah, electricity is so fast, it will work anyhow. It's like I just switch it on and I get the spark. But it's not so easy, because electricity also needs time to run through the cables. And if we have here our electronic control unit signal, yeah, it's like a normal computer. Yeah, you start the signal here, but you have a dwell time to build up the current. Yeah, to build up the current, and then if the current is high enough, you can ignite the spark plug. You get the spark, and then you get the ignition inside the engine. So please take into account, it will not ignite directly. You need an offset here, a dwell time to plan the ignition. Okay, and we can have, I told you, we can have different nozzle designs, different valve designs, and we can also have different positions inside the cylinder. For example, we can have side-mounted ignition. Here, our valve is at the side. It's injected here on the piston. We get a tumble, and afterwards we get our ignition. But you can also have center-mounted injectors. They're a bit more easy. You just install them from the top of the piston, and then the design is also more or less a bit easier. Every hole looks the same, and then you get your ignition. But this design is a bit older design. Many American suppliers use this design. For example, General Motors used it in the past, this central mounted design. Here you can see some pictures of the spray plum. This design of the spray holes is really sophisticated. You can do computer simulations to do the design. For example, this here on the left is a computer simulation I've done with fire from AVL. The code is named, it's a CFD code named fire, and you can inject the droplets, the spray, with the CFD code. But you can also make pictures. You can inject into a dark room with this injector, and then you can make a photo of it. Of course, you need a high-speed camera, and it's not so easy to do it, but more or less it's a photo. And here we compare it with a computer simulation, and I think it looks similar, quite similar. Okay, let's have a look at the diesel injectors. This is also a design I know it really good. I worked for a long time on this design. It's a common rail injector for the N stands for Nutzfahrzeuge. It's civil cars. It's for trucks or vans, for bigger cars. And it's a third generation of common rail diesel injector for vans or trucks. And here the diesel will be inserted here, and here you have a piezo stack. The piezo stack opens here a valve, and then the diesel can inject. Here you see the needle, and the needle opens if you have a high pressure here, and then the valve opens. The needle will be pushed upwards. Here the holes will be opened, and you get injection of the diesel. Okay, and you can imagine here it looks really complicated, and I explained it with easy words, but of course it's much more difficult, and you see a lot of different parameters here. They are all in German. I don't want to explain them in detail, or I don't want to translate them for you. Just mention there are a lot of possibilities to influence this geometry. It's complicated geometry, and you can influence the behavior with many parameters. Okay, I don't want to translate them in detail. Just keep in mind it's a complicated part. Okay, and here you see a diesel spray, injection into a diesel engine, and it looks quite different. The pressure is much higher here. At the gasoline injection, we only had 200 to 300 bars, maybe 400, and the diesel injection, the pressure, the rail pressure is much higher. We have pressures of 1600 bar, 2000 bar, 2500 bars. The pressures are really high, and you can also see that the pressures are so high. If you look at the parts, it's a massive steel part here. It's because of the high pressures. And the spray plum looks also totally different if you compare it with a gasoline spray, because it looks more like a star. Yeah, you can have different number of holes, but it always goes more into horizontal direction. Yeah. Here you see injection after time, after 0.05 milliseconds, 0.25 milliseconds, and so on. And here you see different rail pressures. Yeah, it's nearly 2000 bar at this position. How have we done these pictures? That's sophisticated. You need a glass cylinder, then you can make this kind of pictures, or you make a simulation of this spray plum. You can see another small slide. That's a simulation I have done for a long time ago with ANSYS CFX, and here you see the detailed fluid flow around the tip of the nozzle. The tip of the nozzle is just here at the lower end of the nozzle. It's a really small tip. Yeah. Here the diameter of this tip is only 1.8 millimeters, but we designed the tip really sophisticated, and even if it's so small, it influences the whole spray, the whole efficiency of the engine, and it influences the whole combustion process, and at least the power you get from your engine. Okay, that's another picture, also simulation of different designs of the needle, and here you see the force. The force is always important to ensure the opening. Yeah, the force at the tip of the needle will push up the needle. Okay, and here we have our injection rate of, we have again our common rail injector, third generation. And here you see some real measurements. Yeah, I explained you a lot in theory, but you can also measure all the things. Yeah, you can. Here you see the rail pressure. Here you see the cylinder pressure inside the cylinder of the piston. Here you can see the injection rate. That's the injection rate, and you can see the current and the electricity. And you might see they can have different designs of this injection curve. Designing the injection curves of the injector is a really complicated topic. You can influence the whole behavior of the engine with a type of curve you use. Yeah, if the curve looks more like a triangle or square or rectangle, this will all influence the combustion engine. Okay, here you see small ignition delay. This is the needle lift. Okay. Yeah, I made a bit easier sketch to explain it. Here again, we have our pressure. It's a pressure inside the piston, and we have time of injection. Yeah, we have here, this is the pressure of inside the piston. It can go from about 1 bar if it's open up to 40, 50 bar here at the top. And this is now the pressure when the valves are closed. Yeah, if both valves are closed, this is the pressure inside the piston. Yeah, if you compress it, the pressure goes up to 50 bar. If you open the piston, the pressure will be about 0 bar. But if you now start the combustion, the pressure will be a bit higher, and this will be the work you get back by the combustion. Okay, here the valve closes. It's a more schematic picture I made for you to explain it, but you can also see here the real values, the real measurement. You can measure the pressure inside the cylinder, and maybe here is something I want to mention our school, yeah, the HTW Saar was a really famous school. There was a really famous professor, Mr. Scholz, who invented sensors for pressure, and they were used for engines. Yeah, he was specialist. I think he is retired. Just some weeks ago, he was retired, but he was really famous in designing these pressure sensors. Pressure sensors is a really interesting topic. You can use them for combustion engines or for different other engines. Maybe you have also heard about this airplane crash from Boeing. There was also a pressure sensor on the wings that has to measure pressure. Okay, and to characterize a combustion process, you can also have a short look here into chemistry. You see here, for example, if you have the combustion process starts here, more or less, but it needs some time to start it. Yeah, if you have your fuel injection, here is a fuel injection. This NC, yeah, it's about maybe C7 is hydrocarbon, and this will be combusted, it will react, and it will produce carbon dioxide, it will produce water. Okay, and maybe some emissions. Okay. But if you look at this chemistry, you see it has also some time delay. Yeah, I showed you this time delay in the electric circuit. Here we have a time delay, a dwell time in electricity, and we have a dwell time because of chemistry. Yeah, so you can imagine it is not like in a computer game that everything happens directly. You need some time for the physics, you need some time for the chemistry, and this all causes delays. But you need the power at the right point to get the work from the cylinder. So you have to take into account electric delays, or you have to take into account chemical delays, or even fluid flow delays to get the combustion at the right point. And if you are not good in this design, if you do not understand the chemistry, if you do not understand the electricity or the electric circuits, and you design your injection wrong, you can get serious problems. For example, you see here, you have the cylinder pressure, but if you inject at the wrong moment, you can get at least less work, yeah? And this can destroy the whole engine. You can get knocking of the engine, and you can destroy your cylinder or your valves. And this is really dangerous for your engines. Maybe you know it from some old timers, from the old cars. Sometimes it sounds like an explosion. If you have a knocking or a pre-ignition, then it sounds like explosion, and it can really destroy the engine. Okay. Faster. You can also have this knock sensor, and you can place a knock sensor at the engine, and then you can measure the ECU, the electronic control unit, can really measure if there is a knocking. Maybe if you have bad fuel, yeah, if some water is inside the fuel, or if it's not so good fuel, yeah. If it was a cheap filling station and they sold you a bad fuel, then knocking can occur. But the engine can measure this knocking. Yeah, we have this knock sensor at the engine, and if the ECU measures that your knocking is not really good, then it can change the engine, the control of the engine. Okay, have a short look at combustion and emissions. I already told you we have fuel. Here, I showed you here an example for an hydrocarbon in this. Go back here. I showed you this example, C7H16, but it's only an example. Chemistry is much more complicated. If I really look at the fuel has many different hydrocarbons. So if you look at diesel, or if you look at gasoline, or if you even look at some newer designer fuels, gasoline is not a substance. It's not a real substance. It's a mixture. It is mixed from different components. Yeah, it's mixed, for example, from here alkanes, or from this kind of shorter or longer hydrocarbons, or it's even mixture. It has even mixtures of aromatics, and all these components change the combustion behavior a lot. And in former times, we even had some substances that were not so good. For example, we had a lot of lead. Yeah, the lead were substituted by aromatics. But in former times, when I was in your age, I remember that we had the problem with lead in gasoline. The lead was everywhere in the nature and was really environmental problem. But this was substituted. And yeah, I think this is also still open. Today in the discussion is also design fuel, flex fuel. And here the chemistry can change a lot, the fuel chemistry. For example, if we look at cars from Brazil, in Brazil, flex fuel is really modern. Yeah? A lot of cars in Brazil have flex fuels, and flex fuel is really, it's a really cool technology. You can use alcohol, bio-alcohol in your tank. Yeah? You can mix, if you go to a filling station where you only can buy normal gasoline, you use a normal gasoline, or if you want to use alcohol from bioalcohol, for example, from sugar, you just use this, and the car will measure on its own how the mixture inside your tank is, and then the electronic control unit can change the behavior of the engine depending of the mixture inside your tank. That's really, I think, really advanced technology. Yeah, the ECU will always control and influence your engine, and the ECU is also learning a lot about your driving behavior. For example, if you go to the Autobahn, you drive your car and you drive more, 5-6 minutes in a stable way, then the ECU will start collect data, it will make measurements, and then it will control your engine. Okay, well, this is nowadays already really advanced. Yeah. Okay, here's also another number we already mentioned. It's a lambda value, and of course you calculate the value of lambda depending on the stoichiometry of your chemistry. But this chemical formula is more or less, we call it a lumping formula. It describes, normally there will be hundreds or 300 different chemical equations, but this, we made it more easy. We calculated the easy way, as if we only had this substance, for example. But in reality, we have hundreds of different molecules, and so we have hundreds of different combustion reactions. So normally this equation exists of 100 different equations or so. It's much more complicated in reality. Okay, and there's another problem. if we have a more fuel-rich combustion. Yeah, if we inject a lot of fuel into the cylinder, we have a lot of unburned fuel. It's inefficient. We get carbon monoxide emissions. We get even hydrocarbon emissions at the end. This is not effective. Yeah, this was old cars were used in this way, and so they need a lot of fuel. They need a lot of unused fuel for heat production or for emission production. Yeah, also this emission production, you have to pay for it. Yeah, it's bad for the environment. You have to pay for it because it's unused fuel. It's unused power. So they made the engines more hotter in the past to work more efficient. Yeah, if you work more efficient, you need less fuel. Yeah, let's say 20, 30 years ago, we needed maybe 15 liters on 100 kilometers, and now we can drive with 4 or 5 liters on 100 kilometers. But something else happened. The engines get hotter. And if you have a hotter engine, you produce more nitrogen dioxide. Yeah, we call it NOx or nitrogen monoxide or nitrogen dioxide. You can produce both. So we produce more NO emissions because of the hotter engines, but they are more efficient. This is produced by the air. The combustion air combustion air has about 79% nitrogen and about 21% oxygen. And this, if you have a really hot engine, you will produce nitrogen monoxide by the nitrogen and the oxygen. Okay. Another point is you can have souse. Yeah, you can, if you have incomplete combustion here, you produce more souse. Souse is a aromatic hydrocarbon. It's like a ship. You can, like a small plate, and it is produced from, if you have low lambda values and mean temperatures in the middle, then you produce souse, and you can really see the souse production. The souse is you see it if the flame gets yellow, if you maybe make a barbecue at home and you can see the fire, you can see the yellow color of the fire. This is the souse plum. Yeah? You can have the same combustion without souse, but the souse is visible. You can film it. This was a photo inside the combustion engine. And the souse will also produce a lot of radiation. So if you want to have radiation, you have to produce souse. This is also used in big power plants, in coal power plants. If sometimes they try to produce a big of souse to get a high radiation flame inside the power plant to start the combustion process. Okay, and here you can see an exhaust gas treatment system. It's for cleaning. It's a nitrogen oxide catalysator. Yeah, you have here a lambda sensor. You can have exhaust gas recirculation here to clean. You can recirculate the gas from the cylinder to clean it. Here's your manifold. You have your catalysator, and you can also NOx sensors to control your catalysator. This is a system without area. You can also have a system where also area is injected here at this position, and this helps to clean up the process. Okay, a bit more complicated. Okay, and then we are nearly at the end. Yeah, I want to finish this lecture more or less, but there's one thing I want to mention because I think maybe you followed the discussion here in Germany about nitrogen oxides. Yeah, maybe you know this diesel scandal that happened. Meanwhile, we have Corona. It's much more worse. We had a lot of other bad things in the past, but maybe 4 or 5 years ago, this was the hot topic, the diesel scandal, and it was more or less a starting point to quit all activities in diesel design. I can explain you a lot. I had a lot of colleagues at Bosch. They were working in diesel systems, but no one is anymore working in diesel designs. Yeah, they finished all the activities here. Yeah, that's a bit of a pity because I think it was a really efficient engine. But that was a decision. And I think that's even if you should, maybe I think it's a bad decision, yeah, because if you have some problems at a point, and then you say, oh, there are some problems, I don't work on it anymore. You put your head in the sand and you don't care about it anymore, and you fire all the people that were working on this topic. That is not the right decision. Yeah? If you have a problem somewhere, you must work harder to solve the problem. It's not the right decision to say, okay, we fire all the people that work in this topic. We do not work anymore this topic. I think that was not the right decision. And you're all clever people. You're all engineers. You know how to calculate. You know about mathematics. And in my opinion, this discussion about the diesel engine has really much to do with mathematics, because all the people that made decisions, they were not able really to calculate what was really happening. If you look at this diagram here, you see this is the limiting value for nitrogen oxides. It's 40 micrograms per cubic meter. This is a limiting value in the EU. And this value is so low. Yeah, someone calling me, but I must put it off. Yeah, we have. Okay, I just want to explain you this last slide and then we are over, because that's important for me to explain it. Yeah, this is the limiting value in the EU. And I worked for over 10 years, 12 years. I was designer for diesel engines, and we all knew that this limiting value was too low. Everyone knew it. Yeah, we knew it from the beginning when it was planned, but no one was able to stop this. Yeah, we all knew this limiting value was too low. And here is a measurement. Yeah, that was a measurement that caused a scandal in Munich. Of course, we had the value in Munich was twice as high as the limiting value, or the value in Stuttgart was twice as high as the limiting value. But let us look how much is 40 microgram per cubic meter. And I told you, you're all clever persons. I made this short calculation for you. If we have how much is 40 micrograms per cubic meter? If we have a cubic meter of air, and a cubic meter of air is about, let's say, 1.2 kilograms. Yeah, we have 1,293 grams. That's a cubic meter of air. And if we now compare 40 micrograms with 1.2 kilograms, we get a value that is that has here 1, 2, 3, 5, 6, 7, 8. So we have a really, really low value. And the nitrogen oxide, it's not poisoning, it's not radiative, it's just a bit hazardous. It's not poisoning, yeah, and it's so a low value. If you compare it with I took this value. If you compare it with the amount of one cigarette you get from the amount of nitrogen oxide you get from one cigarette, you get 1,200 micrograms only from one cigarette. So if anyone who ever made a barbecue or ever smoked a cigarette has millions of micrograms more than that is allowed for diesel engines. So this value is really a crazy value, in my opinion. It's just to kill this technology. Okay, then I have some more slides, but I think we can go a bit faster. Yeah, here we have also this exhaust gas treatment. We have sensors. Yeah, we have different driving cycles. That makes it also a bit difficult. We don't have one point, one step on the gas pedal. We have, if you maybe drive from Stuttgart to Hamburg, or if you drive from Helsinki to Lappenranta, you don't have one stable point where you press on your gas pedal. You have a lot of different points. That makes it much more complicated, this design. So in my opinion, a good new future design would be an electric car with a range extender, yeah, where you have your combustion engine in a stable mode and you use it to produce electricity, and then you have an electric motor for driving. This will be a really cool design. Hopefully they will do it sometime. Okay, and also I want to mention a bit about, go a bit faster. You have a lot of different engineering tools for measurement. You have, for example, design with a cut of the spray plums. You can have optical engines. You can have single engines or multi-cylinder engines and can make measurements. And you have, as an engineer, the analysis part. For example, here for 0D simulation or 1D simulation, for example, with Amazon, or 3D simulation of spray plums, for example, with ANSYS X or AVL Fire. Okay, and we have the test cycle. Yeah, I go a bit faster. The only thing I want to mention here, I explained you, there's not one test point. The engine is not designed only for one point. The engine must be designed for several different scenarios. Yeah, you must, if you start with your car and you drive slow, the engine must be efficient. But the engine must also be efficient if you have full speed at the motorway. Yeah, so the engine must be designed for many different test cycles, and you do not have one optimal point. You should have a kind of map, yeah, an engine map. You should have different rotations of the crank, different pressures inside the cylinder, and for all the different pressures inside the cylinder and for all the different rotations of the crank, you must have regions of optimal behavior. Okay, you can imagine that's a lot of work done. Okay, and I also want to mention the 3D CFD simulation. CFD simulation is also something I teach you in fluid dynamics. It is really necessary to design combustion engines, but it is also necessary for many other kind of engines or fluid energy machines. Okay, so I go a bit faster. Yeah, maybe we use this as a last slide. Yeah, it's I made this joke a bit for design of injectors, but you can use it for engineering in general. You have to take into account, if you have a system, you have to take into account all the influences. Yeah, you cannot say, oh, we design only this part and we do not care about this part. Yeah. Otherwise, you can't. A system is always a bit like this kind of whip. Yeah. If you take care about one problem, you also have to look at the other side, of the problem to get a system working. Yeah. Okay. I think that's enough. Yeah, we have some slides more. Yeah, here about the efficiency, but I think that's okay. Time is over. And Mr. Luther, please, can you stop the movie?